Imagine being able to look directly into the heart of one of the most mysterious objects in the universe, the neutron star. I can tell you right now, neutron stars are even more incredible than you think. What you would see there is beyond the scope of your mind and puts you in touch with forces that your brain simply cannot comprehend. These fascinating objects are incredibly dense, fast, and absolutely deadly. But where do neutron stars actually come from, and are they really a serious threat to us? Neutron stars are the remains of very large, collapsed stars. After the final bang, the stars disappear in a huge explosion. The matter of the star is hurled through space, gases and heat billow in an inferno that is hard to imagine. Then, in the place where the star has been for millions or billions of years, all the remaining remnants of the stellar giant collapse, and a neutron star is formed. This object is no larger than 20 to 40 kilometers, or, in other words, tiny compared to the star, which was at least several 100,000 km in diameter. In this place made up of the remains of the star, the most bizarre object humans have ever heard of is formed. It consists of an incredible density. A teaspoon of the elusive substance of a neutron star would weigh an incredible 8 billion tons. But how exactly do these objects form? We can only partially answer this question, because we still don't know everything about the processes during stellar collapse. Electrons are pushed into the nuclei of atoms, where they fuse with protons to form neutrons. These stars, therefore, consist mainly of neutrons, which explains their name. In physics, neutrons are subatomic particles which, together with protons, form the nucleus of an atom. They have no electrical charge, so they are neutral and are slightly heavier than protons. Neutrons play an important role in the stability of atoms as they balance the repulsive forces between the positively charged protons in the nucleus. Without neutrons, the protons would repel each other, and the atomic nucleus would fall apart. The mass of neutrons is due to their internal structure. Compared to other subatomic particles, they are relatively heavy. Neutrons belong to the so-called baryons, a group of particles composed of 3 quarks with strong interactions. So, if you were to look directly into the neutron star, you could see the shape of matter with the highest known stable density. Details about the inner structure of these objects are just as mysterious and secretive as the interior of black holes. The two phenomena are closely related and yet quite different. A supernova can form a neutron star or a black hole, and its minimal amounts of mass decide one way or the other. Some scientists believe that the interior of a neutron star consists entirely of normal neutrons, while other theories suggest that inside the star, the components of the neutrons, quarks and gluons, actually move freely in a kind of plasma. It's possible that the interior of these stars consists of even more exotic forms of matter, such as the hyperons, which in turn are composed of strange quarks. These particles are strange because they move in a way that can hardly be described scientifically. Neutron stars are born in huge Type II supernova explosions, although the actual birth is rarely observed, as it happens on average only once a century in the Milky Way. In other words, the formation properties of these objects cannot be observed directly. Fortunately, however, neutron stars are often visible as radio pulsars, so we can study them. Neutron stars are potential sources of the dreaded gamma bursts. If such a flash were to hit the Earth, our ozone layer would probably be destroyed within seconds, and the Earth would slowly turn into a blazing hot inferno. But we can give the all-clear: these flashes do travel extremely fast over long distances. Yet these events are so rare that we are safe. Neutron stars versus black holes, which do you think is heavier? The neutron star or a black hole? With masses between 5 and 100 solar masses, black holes are initially heavier than neutron stars, which have 1.4 and 2.5 solar masses. But neutron stars have an extremely high density, where a teaspoon of matter can weigh billions of tons. Their density is close to the extreme density of atomic nuclei, concentrated in one spot. Neutron stars, thus, weigh more than most areas of a black hole. The singularity at the center of a black hole is probably an exception. There, the density and weight theoretically approach infinity. Neutron stars and black holes are the endpoints of stellar life, but their properties could not be more different. And it is precisely this fact that gives researchers food for thought. A neutron star is formed from the remains of a collapsed star that originally had around 8 to 20 to 25 solar masses. These stars usually belong to types O and B, which are among the most massive and hottest stars in the universe. They are often brightly shining parts of star-forming regions and young star clusters. A black hole is also the end product of a star with an original mass of over 20 to 25 solar masses. These stars are usually also of type O and B, but at the upper end of the spectrum in terms of mass and luminosity. They are very rare compared to less massive stars. Black holes are patches of space in which mass is so densely concentrated that gravity becomes extremely strong. While neutron stars are observable through their strong magnetic fields and the emission of electromagnetic radiation, including visible light, X-rays, and radio waves, black holes remain mostly mysterious and invisible to us. They only reveal their presence through the gravitational influence of other objects or through the sometimes brightly glowing dust disks around the event horizon. Neutron stars, with their extreme magnetic fields and rapid rotations, are like cosmic lighthouses that emit their secrets in the form of pulses of radiation. Black holes, on the other hand, are the great devourers of the universe, whose singularities still challenge the limits of our understanding of physics. Both are fascinating witnesses to the incredible forces at work in the universe. And it may be hard to believe, but sometimes neutron stars and black holes collide. Then, a cosmic spectacle is unleashed that shakes spacetime and generates enormous gravitational waves, which in turn affect the entire galactic environment. Even more incredible objects, pulsars and magnetars. Neutron stars are undoubtedly among the most fascinating phenomena in astrophysics, and among these incredible manars, there are two special types that are even more unusual, pulsars and magnetars. Both are closely related, as they are also clearly formed from the collapse of massive stars, but their individual properties differ significantly. Let's take a look at pulsars first. These rapidly rotating neutron stars were first discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish. Pulsar comes from pulsating star and refers to the emission of regular pulses of radiation. These powerful pulses are caused by the rapid rotation of the star, whereby the axis of a pulsar's magnetic field does not coincide with its axis of rotation. The radiation generated at the magnetic poles is emitted into space as a recurring and pulsating signal. Some pulsars, such as PSR J1748-2446 AD, reach breathtaking rotational speeds of up to 716 revolutions per second. Magnetars impress with their extremely strong magnetic fields. Magnetar, originated from the combination of magnet and star, these neutron stars have the strongest known magnetic fields in the universe. They are up to 1,000 times stronger than those of typical neutron stars and up to a quadrillion, or 10 to the power of 15, times stronger than the Earth's magnetic field. These enormous magnetic fields generate intense electromagnetic radiation, and in addition to X-rays, can send dangerous gamma rays into space. A well-known example of an extreme magnetar is SGR 1806-20, whose eruption in 2004 was the strongest radiation explosion we have ever observed. Pulsars and magnetars are also very small. Their density is even higher than that of normal neutron stars, which also makes their properties more extreme. The most extreme neutron stars are spectacular, extreme, and among the most wild phenomena in the universe. And here again, we find a fascinating fact: no neutron star, pulsar, or magnetar exists anywhere near twice. Researchers have now identified hundreds of these objects in the vastness of space, and they all fascinate us with their different properties and peculiarities. RxJ 1856-57 is still a rather peaceful fellow among the neutron stars, fortunately, because it's the one closest to Earth, only around 400 light-years away. RxJ 1856-3754 rotates relatively smoothly and shows no strong magnetic fields or bursts of radiation. With a diameter of only about 14 kilometers, it's also one of the smallest known neutron stars. Despite this coziness, its surface temperature is around 700,000 degrees Celsius, which is still relatively cool for neutron stars. With the Holt-Taylor pulsar, or PSR J1915 plus 1606, we have an extreme double system consisting of a pulsar and a neutron star, discovered in 1974 by Russell Holt and Joseph Taylor. It was the first system in which gravitational waves were indirectly detected, and this discovery even earned the two researchers the Nobel Prize in 1993. The pulsar rotates around 17 times per second, and the two are slowly approaching each other. What will happen when the two meet is still unknown. We do not know whether the two will neutralize each other, generate extreme tensions, or combine to form a single, even more powerful object. Researchers simply call the pulsar PSR B257 plus 12 the Lich pulsar. Lich is famous for its exoplanet. This poor planet is, so far, the only planet that has been sighted in the vicinity of a pulsar, and it's a shocking example of what happens when matter gets close to a pulsar. The planet still exists, but its surface has been so devastated by the extreme radiation that it looks more like a planetary corpse. Researchers are still puzzling over whether this unfortunate planet survived the violent supernova explosion of its star or whether the neutron star later captured and destroyed a vagabond planet. The record for the fastest rotating neutron star is held by the aforementioned PSR J1748-2446 AD. It is located around 18,000 light-years from Earth in the Terzan 5 globular cluster, and with its incredible rotation rate of 716 revolutions per second, it is an extreme example of the incredible physical conditions of neutron stars. Around 9,000 light-years from Earth, in the constellation of Scorpius, we find another curious example of a neutron star. The X-ray binary star system Scorpius X1 shows us that there is almost nothing in the universe that does not exist. This neutron star forms a bizarre binary star system in which the normal star has to give up more and more mass to its extremely fast-rotating companion, which leads to intense X-ray radiation and will one day destroy the star. Subscribe now, because the best videos are yet to come.